Good morning, everyone, and welcome to day 2 of DARPA Forward. To kick off today, I'm going to share with you some of the work that we're looking at in enabling next-generation communication systems. Why communications? We've developed this insatiable appetite to communicate, not just voice, data, but now real-time streaming video. As an example, everyone is pretty much walking around with one of these, a smartphone. In fact, we want to basically be connected all the time, instantaneously. In fact, there's probably people watching this meeting on Zoom on their phone so they can interact. And we don't want to just communicate locally with the global, with the now LEO satellite systems. We're looking to be able to communicate instantaneously anywhere on the face of the Earth. Now, this is all about people-to-people communication, but there's emerging areas of looking at things communicating. For example, autonomous vehicles, where you get to a point where cars or vehicles on the highway are sharing their sensor data to overall improve highway safety and more efficiently operate our highways. The DoD is interested in sharing a lot of information and data from sensors on the ground, in the sea, undersea, in air, and in space to create a smart battlefield, overall to improve situational awareness for the warfighter. And then there's the exciting area of virtual reality and augmented reality, where we want to create this immersive experience so that you can pretty much be anywhere. You can think of it, you're time traveling or going almost anywhere. Now, what do all these applications have in common? The need for higher and higher data rates, higher and higher bandwidth, and very low latency for moving this data. But what we're also finding is we have this big challenge. As we try and do more and more and communicate more and more, we're trying to do a lot more diverse missions in very complex environments. And in fact, the portion of the electromagnetic spectrum that we're using for communicating is becoming crowded. In fact, so much it's becoming congested. I can almost look at it as an analogy to, it's like the highways around our cities during rush hour. At times, the traffic moves very fast. At other times, it comes to a complete stop. Think of that as that's what's happening to your data or your video transmission, coming to a complete stop. So what we need is a solution. And essentially, we need a new higher speed data highway. And so how do we begin looking at that? I think there's a lot of opportunity if we begin moving up and up in frequency. Today, we live in this space in the lower left of this chart where our mobile communications are our 4G or 5G networks. But even the commercial suppliers are just finding that, you know what, there's not enough bandwidth and we can't move enough data at this frequency. So they're beginning to explore the millimeter wave, so 5G millimeter wave for communications. But why stop at the lower millimeter wave frequencies? Why not move all the way up to the upper end of the millimeter wave spectrum, a frequency band known as G-band between 100 and 300 gigahertz frequencies, where we can get to very wide bandwidths. There's a lot of available spectrum. We can go to very high data rate communications to support all this growing insatiable need. So why can't we do this today? The simple fact of the matter is the electronics, particularly the RF electronics, doesn't exist to operate at these frequencies and particularly operate efficiently at these frequencies. So what do we begin to do? Everyone is aware of the great advances in silicon technology. In fact, in silicon RF technology, where you can begin building compact RF ICs or compact radios. The example here is a radio in a package that operates in the low millimeter wave frequencies. The challenge is that the silicon technology is not very efficient. So you can think of, I'm using it as in a part of a communication device, your talk time isn't going to last very long. Now, there happens to be a class of semiconductors, the compound semiconductors, that have superior RF performance that can really drive performance up at the millimeter wave frequencies. The challenge is you can't get the compaction or integration density with these. So how can we get the best of both worlds? And this is where the area of 3D heterogeneous integration comes in. What I mean by heterogeneous integration is the mix and match of different materials, devices, functionalities into a single package, or importantly, if you can even do it in a single wafer or in a single chip to create new function or capabilities. And in fact, 3DHI is one of the themes of the Microsystems Technology Office, the office that I'm a part of, and it's also one of the themes for the Electronics Resurgence Initiative. In fact, we have a BAA out on the street now called NGMM, Next Generation microelectronics manufacturing, which is looking for innovative ideas on how to do manufacturing of 3D heterogeneous integrated systems. There's also another area that we're looking at, and there's a program I have called ELGAR, or Electronics for G-band Arrays, which is really focusing on that G-band frequency spectrum with how can we make the compact and efficient electronics that operate and would enable us to have systems that operate in that frequency band. And the picture that I have on the left is just kind of showing an example of what one of these radios would look like. And each of those gold spots is an antenna to create a phased array. The size of these are less than 1 millimeter, so we'd have to get all the electronics to fit in a 1 millimeter square area. To put this into context, that little radio would fit on Abraham Lincoln's nose. So what I would like to leave you with is an important area that we're looking at is 3D heterogeneous integration as an enabler for next generation communication and sensor systems. If you'd like to learn more or have ideas you'd like to share, come see me at the DARPA timeline during one of the breaks. Thank you.